Okay, last time we started talking about chapter 3, which again is exam 2 material. Um, we're still really talking about bonding here. We're going to be talking about bonding really for next couple of chapters, this chapter and the next one. They sort of go together, obviously. Um, and we've got into last time sort of the different types of bonding that we do come across. We have our ionic bonding, which is always between a metal and a non-metal. And really the main way that ionic bonding basically occurs is we pretty much have an electron transfer. So we have electrons that are transferred from the metal. The result of that is the metal becomes positively charged or a cation. The non-metal, because of all those periodic trends that we talked about previously, want to really accept those electrons. So they accept those electrons, they become negatively charged, and now we have an ionic compound that's been formed as a result of a positive negative attraction between each other and electrostatic attraction basically holding that together. The importance of an ionic bond, as we talked about, is there is absolutely no sharing of electrons happening there. So we get a complete transfer of those electrons from the metal to the non-metal. And that's different than sort of covalent bonding. And covalent bonding, it's really between two non-metals. So as we've talked about last time and before, obviously the non-metals are pretty much in the same location on the periodic table, which means they share very similar sort of periodic trends. And the similarity that they have is that essentially they both really want to A, keep their electrons, and B, they kind of want other people's electrons. So they share those similar sort of trends. So as we talked about, basically what they end up doing is they settle on some type of sharing of electrons, which makes a covalent bond different than an ionic bond in that sense. There's actually sharing of electrons between the two elements, or atoms of the two elements. But there is some different sort of levels of sharing and our covalent bonding there. And the levels of sharing is basically two. One is either you got kind of perfect sharing or equal sharing of electrons, I guess is a better way of wording that. With equal sharing of electrons, we get what is referred to as a nonpolar bond. Again, sometimes called a nonpolar covalent bond. Again, most people would just call it a nonpolar bond. And that implies that the electrons are being shared and they are being shared equally between the two atoms of those particular elements. Now, we also have a polar bond and a polar covalent bond, which again is just oftentimes referred to as a polar bond, is again sharing of electrons between those two nonmetals. But here we have the sharing being unequal. So the electrons are basically hanging out kind of on one side of the bond more than the other side. They have not completely like jumped all the way over there that they've been transferred. There's still some aspect of sharing happening, but it's definitely not equal sharing of electrons like we see in a nonpolar bond. Now, those are sort of the three sort of types of bonding that we talked about. We could also use something like what we're looking at here on the screen and sort of where we finished up last time, which is the electronegativity values. Remember, Pauling basically assigned electronegativity values for all the elements, runs from like 0 to 4, 4 being the most electronegative, and that's our fluorine top right corner of the periodic table there. And you basically could take the electronegativity values and kind of subtract them. And you subtract the two values from the bond that you're looking at. And usually you take the larger number minus the smaller number, so you get a positive sort of overall number when you subtract. But if you do this subtraction between the two elements there within a bond, and you get a value somewhere between 0 to 0.4, that is considered a nonpolar bond. It's considered sort of equal sharing of those electrons if you get that sort of value. If you get above 0.4, which probably would put you at about 0.5 in most cases, to below 2, that will give you some type of polar bond. And typically above 2, and as we talked about last time, again, just a general guideline, typically above 2. There are some exceptions if you that are not necessarily above 2, but are still ionic. They would have an ionic bond. As we talked about last time, you just definitely actually for an ionic bond really don't even need these numbers. As soon as you can recognize a metal and a non-metal basically coming together, it's a pretty safe bet that you're dealing with an ionic bond. But it can be very helpful for covalent bonds and sort of figuring those things out as well. A couple of important things that we talked about with this chart was the idea that, if you do have obviously the same element involved in the bond, it's going to be a nonpolar bond. You're going to get a difference of 0. And that's also sometimes referred to as a pure covalent bond. But it is also possible that you could get a difference of 0 with 2 different elements based on their location on the periodic table, sometimes referred to as a diagonal sort of rule or diagonal relationship. And again, if we kind of look over here, we see that with carbon and sulfur, they're diagonal to each other, and they do contain basically the same sort of electronegativity value. Same thing there with nitrogen and chlorine, Te and phosphorus. You get this sort of diagonal sort of relationships coming down this way as well. And so, it is definitely possible to perhaps have 2 different elements that actually will share those electrons equally. And again, that occurs because of that diagonal relationship. One is higher up on the periodic table, but one is sort of equally over further on the periodic table, and it sort of cancels out their differences in terms of electronegativity. Now, we also talked about that, there's a lot of situations where you might not even, again, need the actual numbers here for electronegativity to make your determination in terms of whether it's a polar bond or a non-polar bond. And that's especially dealing with, obviously, covalent bonding. And when we have either 2 elements that are in the same period, like I think we looked at there, carbon and oxygen. So carbon and oxygen, again, in the same period on the periodic table, without even looking at the numbers or knowing the numbers, just knowing the general trend that further to the right is more electronegative, you can make a pretty safe bet that oxygen should be more electronegative than carbon, and you would have a polar bond, and it would be heading towards the oxygen. Also, if you're comparing 2 elements there that are in the same group going up and down on the periodic table, you could also use the general trend pretty safely to make that determination whether or not you have a polar bond or not. So again, I think we looked at oxygen and sulfur in this example that we did here at the end. And again, looking at the periodic table, we see oxygen is higher up in the group than sulfur, and that should indicate that oxygen is more electronegative than sulfur. And again, because they're in the same group, you can make a pretty safe bet that it is going to be a polar bond, and oxygen should be more electronegative. So there's a lot of instances where just the general trend in electronegativity can be used to make a pretty reasonable assumption in terms of whether or not you would expect a polar bond or not. We also talked about, again, when we do have a polar bond, what that really means is, again, we have unequal sharing of electrons. And what that creates in that bond is a side of the bond that's more positive and a side that's more negative. So as we talked about with HF, because fluorine is more electronegative, the electrons are hanging out towards the fluorine more, making that side partially negative. While the hydrogen is becoming partially positive because the electrons are sort of moving away. Again, they're partially positive and partially negative, like we talked about last time, because the electrons are still being shared, so they haven't been fully transferred. But it does create this sort of charged situation that occurs within that bond, where one side's more positive and one side's more negative. We could represent those with that delta positive, delta negative sort of symbols, or we could sort of do it with the arrow, where the arrow points to the more electronegative side, and then that arrow would have the little positive sort of guy on the back end of it, and that goes to the one that is least electronegative. Any questions on any of that stuff there? Okay. So as we've been talking about, obviously atoms with really widely different electronegativities will typically lead to an ionic bond. And again, as soon as you see that metal, non-metal, pretty safe ionic bond sort of situation. And atoms with very similar sort of electronegativities will tend to form those covalent bonds, either polar or non-polar type bonds. Again, only a small sort of change in that sort of electronegativity values between them, really because they're all sitting in the same sort of side of the periodic table. And that brings us back to, you know, kind of what we talked about before as to really our two sort of guys that are going to be ionic and covalent. Metal, non-metal for ionic, are two non-metals there for our covalent bonding. So a couple other sort of considerations and stuff that we sort of talked about. As I mentioned before, those cutoffs, you know, they are fairly standard in terms of where we cut off in terms of the difference in electronegativity values. And again, as we touched upon yesterday, that sort of value of 2 or more is typically what we have for an ionic bond. The rule applies to most, but again, not all ionic compounds will maybe have a above 2 sort of value. And that's why we really do sort of default to, oh, it's a metal, non-metal, so it's definitely going to be an ionic bond. Sometimes we talk about sort of bonds, either polar, ionic, and stuff like that, by using the term sort of percent ionic character. So if a bond has 100% ionic character, then it definitely is an ionic bond. Heading down to sort of 0% ionic character, where we pretty much have more of a covalent or non-polar bond sort of happening. So here's just a table of the differences there. Again, in a 0% ionic character, you know, we have basically a non-polar bond or a pure covalent bond. We have a large percent ionic character that's an ionic bond somewhere in the middle, obviously our polar bond. So this is sort of what we were talking about the other day as well. You know, these are sort of the extremes where over here we got nice perfect sharing of electrons. Over here we have no sharing of electrons. We have a transfer of electrons. And here we have sort of in the middle, you know, we have definitely not equal sharing of electrons, but we haven't hit the point where that unequal sharing of electrons is so bad that the electrons decide to basically jump ship and transfer. So we got some degree of sharing sort of happening. So now we're going to talk about actually how to draw Lewis structures for really covalent bonding, to show covalent bonding. Now there's several different ways that sometimes people draw Lewis structures or write Lewis structures. But I will say that if you follow these steps, you really should end up with probably a fairly good picture when it's all said and done. You definitely want to kind of follow these sort of steps in drawing these Lewis structures. You don't want to do what sometimes I call kind of piecework. And piecework means you kind of draw out all the Lewis dot symbols or electron dot symbols, try to figure out where each electron sort of goes. And a lot of times, if you sort of do it that way, like, oh, I need to put some electrons here or bonds here, you typically will end up with a picture that has too many bonds, not enough bonds, too many electrons, and stuff like that. So typically, again, if you sort of follow these rules here that we're going to kind of go through, it really should lead you to sort of a pretty good picture when it's all said and done. A couple of important things to remember, right, as we draw these things are really the two sort of rules. Remember that pretty much everybody wants 8 valence electrons, right, which is our octet rule. The exception, right, would be hydrogen, which should have only 2 electrons when it's all said and done. That is, again, what is sometimes referred to as the duet rule. So one of the most important things in terms of maybe drawing Lewis structures is obviously the way that you put it together. And that is sometimes referred to as sort of thinking about the skeletal sort of structure of the compound. sort of what atoms should go where. There are some rules that help you sort of determine where you should sort of place certain atoms versus other ones. Some of the general rules are, in general, the least electronegative atom is in the center. So I would say probably in most of the things that you would draw probably in this class, there's like a center atom, and then everything else is sort of attached to the center atom. There definitely can be more than one center atom in some cases, but probably commonly most of the stuff that you'll come across in this class will be one center atom with other things attached to it. So we really want the least electronegative guy to be in that center atom. We also typically find hydrogen and fluorine on the outside. They never basically occupy the center positions, and that's for two reasons. One reason is the least electronegative atom should be in the center, and clearly from what we've just been talking about, fluorine is the most electronegative atom, which means it should not be in the center. Secondly, hydrogen should not be in the center, because if hydrogen again is in the center and you decide to attach something else to it, now my hydrogen has way too many bonds. Remember, hydrogen pretty much should always look like that. Basically one line in, hydrogen on the outside. Again, no dots or anything around hydrogen. Just needs 2 electrons for it to get to helium's configuration. Once you sort of have in your head sort of how the structure should be sort of laid out, the next almost really important thing, probably the most important thing, is you want to count up the total number of valence electrons there is in that particular compound or ion, whatever it may be. Now, if we do have a polyatomic ion, for example, that does have a charge, we do have to adjust our electron count. So a reminder that if something has a positive charge, that means that it lost electrons. So you need to adjust your count in terms of electrons down by the number. So if it had a +2 charge, you should take off 2 electrons. If something had a negative charge, so if you come across a polyatomic ion you're drawing that has a negative charge, then it means it gained electrons. So you need to add that to your grand total there. Otherwise, again, your picture will be off by the number of electrons. Number 2 here, the total number of valence electrons is really the most important thing, because when you are all said and done, your picture has to have exactly that many electrons. You cannot have any more electrons than that. You cannot have any less electrons. It needs to hit that number of electrons exactly on that nose. Once you've done that, now we got the sort of arrangement of how everything is put together. We have how many total electrons we should put in that picture. The next thing you should do is go from the center atom to each of the outside atoms and basically make one line or a single bond. I personally use lines. Again, you could use dots instead of lines, but I use lines. You want to basically draw a line from the center guy to each of the outside guys. And when you do that, that's going to use up a certain number of electrons. So each line that you make or bond that you make is 2 electrons. You would count up how many electrons you just used, and you would subtract it from your total number. And all the remaining electrons that you have, once you do that, they go on all the outside atoms first, and they go on in pairs. So you go on the outside atoms and you put them on in pairs until you fill up an outside atom with 8 electrons to complete the octet. Then you move on to the next outside atom, fill it up with 8 electrons, fill it up with 8 electrons, until you filled up all the atoms on the outside with electrons. If you've now made single bonds from the central atom to the outside one, you filled up everybody on the outside one with electrons, and you still have electrons to go. Then you put those electrons on the center atom as dots in pairs. At that point, you should run out of electrons at some point. Once you placed all your electrons onto your picture, the very last thing that you should do is go around and make sure that every single atom in that structure that you just drew basically meets the octet rule. And it's at that point that if you go around and you place all your electrons there and you look and you see that there is a atom that does not meet the octet rule, it's at that point that you should try to fix it by making a double bond. And if a double bond doesn't sort of fix it and there's no more double bond possibilities, then you should make a triple bond at that point. So I think I might have mentioned it the other day as well, but it's very common sometimes when people go to draw Lewis structures is they're very anxious to double bond things right out of the box, kind of triple bond things right out of the box. And you really shouldn't do that. A lot of times that will lead to perhaps not the best sort of structure that you draw or an incorrect structure. The idea here is you can think about double bonds and triple bonds as a way to fix a situation where somebody does not meet the octet rule. And that's where you should try to apply double bonds or triple bonds to your structure. Again, you shouldn't double bond or triple bond right out of the box. Clearly, that last rule there also applies to hydrogen, and hopefully at that point, hydrogen should only have, again, basically just one line to it. Any questions on those steps? All right, so let's take a look at one here together, just to kind of see again, kind of going through these steps and what we should end up with. Let's take a look here at NF3. So if we were to draw NF3, one of the first things you want to do, or really the first thing I do personally, is I really do count up the total number of valence electrons. So remember that the number of valence electrons equals the group number. So that is really the easiest way to figure out, how many valence electrons you should be drawing in your picture. So if I go to periodic table, I see nitrogens in group number 5, which means that there are 5 valence electrons for the nitrogen. There are 3 fluorines here, and each fluorine's in group 7, which means it has 7 valence electrons. So that is 21 and 5, which means 26 valence electrons. So this 26 valence electrons that we just calculated from the formula here means that we should end up with a picture that has exactly 26 electrons on it for it to be correct. We want to think about logical arrangement here. We could use our rule that the least electronegative atom, which in this case would be nitrogen and fluorine's in the same row, and fluorine is the most electronegative, and fluorine cannot be in the center. So we know pretty much nitrogen should be in the center, fluorine should be attached to it. Logically speaking, in most cases, if you have sort of one element and multiple of other elements, usually the guy with one sort of atom there is in the center and everybody else is attached to it. So sort of the skeletal arrangement we should have in this is nitrogen should be in the center. We should have some fluorines on the outside. And the question may be, I put the fluorine down here. Could I put the fluorine up on top? And the answer is yes. I could put it in either location. I could have done up on top or on the bottom like I did. Is perfectly okay either way. Now that I have my total number of valence electrons, I got my sort of logical arrangement. The first thing I want to do is make a simple single bond from the center atom to each of the outside atoms. And again, you can use dots here or lines. I'm personally going to use lines to show the bonding electrons. At this point, I have now used 2, 4, and 6 electrons, which means I should take 6 away from that. And I really have 20 electrons to go in my picture. These 20 electrons go on the outside atoms in pairs. So I'm going to go 2, 4, 6. That's going to fill up this guy with 8. Then that would be 8, 10, 12. That will fill this guy up. 14, 16, and 18. That will fill this guy up. At this point, if I look at how many electrons I've placed on my picture, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. I still have 2 more electrons to go, right? I need 26. I have filled up everybody on the outside. Then once I do that, I will then go to the center atom, and on the center atom, I should put some electrons there, again in pairs. And now at this point, I've put on there 26 electrons total, which is what we're looking for. The last thing we want to do is go around and make sure everybody has 8. So that's 2, 4, 6, 8. So he's good. 2, 4, 6, 8. Good. 2, 4, 6, 8's good. And for our nitrogen there, we have 2, 4, 6, and 8. Everybody here has 8 valence electrons. They all meet the octet rule. They are perfectly good, and that would be the correct structure. I'll just redraw it real quick since I just highlighted all over it. Should look something like this. Any questions on those steps there? Again, you can see I didn't decide I should be double bonding or triple bonding or something crazy out of the box. Again, I just followed those rules. And in this case, since everybody met the octet rule, there's no need to double bond or triple bond anything. Again, we want to do that if we do not meet the octet rule. Any questions on that? All right, so why don't you try this one, see what you come up with. Let's do carbonate. So why don't you draw the Lewis structure there for carbonate, take a couple minutes, and we will talk about it. Okay, so let's take a look here, see how we're doing. So again, you want to kind of approach all these guys the same way. One of the first things you really should do is figure out total number of valence electrons. That's really, sort of the important thing. So we look at carbon, which is group number 4 on the periodic table. So that tells us we got 4 valence electrons for it. There are 3 oxygens. Each of the oxygens come from group 6 on the periodic table, which means there's 6. And now we have a overall charge here on carbonate of -2. So as we've been talking about sort of ions, minus obviously means that it's gained electrons, and 2 is how many electrons it gained. So in this particular case, we do need to actually add 2 to it. And again, that is for the charge. If we had a +2, we would be subtracting because that means it lost electrons. But here with the -2 means it basically gained electrons. And that's going to give us a grand total of a lot of math, but we'll go with 24 valence electrons in this particular case. Now, when we look at these two, again, we have a situation where we have basically 1 carbon atom. We have 3 oxygen atoms. So usually it's a pretty safe bet that the guy with 1 is in the center. But we also kind of know it's going to be in the center because if we look on the periodic table, we have basically this run here. And we see that carbon is further to the left than oxygen. Oxygen obviously should be more electronegative, which means carbon being the least electronegative should really find itself in the center. And we do a carbon there in the center. Again, we're going to just kind of place around our carbon there are 3 oxygens. Just like in the previous one, if you wanted to, you could have drew the oxygen on the bottom. It's perfectly fine as well. We are at this point going to do 1 single bond to each of those oxygens. That again is going to use up 6 electrons, 2, 4, 6 electrons. That leaves us something like 18 electrons to go. 18 electrons will go on the outside one again in pairs. So 2, 4, 6, 8, 10, 12, if I get it there, 14, 16, and 18 in this case. At this point, we have now placed, I believe, all 24 electrons on our picture. We now need to make sure everybody has pretty much met the octet rule. If we look at sort of everybody here, oxygen 2, 4, 6, and 8, so it's good. Every single oxygen is the same, so they're all good. But we do run into a little problem here with carbon. That's 2, 4, and 6 electrons. So carbon here is actually short of the octet rule. So it is not good, this picture, in this sense. We need to fix that. We need to get basically carbon to the octet rule. And we need to do that. You may be saying, all right, well, why don't we just, lay up a couple of electrons there? Now he's got 6 and everything's good. Everything's not good in this case, because by you just putting the electrons there, you have now made it 26 electrons in here, which is definitely not 24. So you cannot just basically put in some electrons because you're short. Otherwise, you will have too many electrons, obviously, in your picture. So this is a situation where we do need to make a double bond and see if we can fix the problem by doing that. So again, when we make the double bond, you may say to yourself, all right, I can make a double bond between this carbon and oxygen, or this carbon and oxygen. And the answer is you can, because they are all exactly the same oxygens on the outside. You could actually make a double bond anywhere you wish. I'm going to double bond the top guy here. And you may say to yourself, okay, I could just make a double bond. And if you just draw the double bond like that, you're going to run into the same situation. I now have 26 electrons. In addition, this oxygen now has 2, 4, 6, 8, 10 electrons, which is too many. So when we do make a double bond, which is what we need to do, we actually need to take a pair of electrons, say this pair of electrons, and we basically need to bring those pair of electrons in to make the double bond, which means we need to kind of erase those electrons when it's all said and done. So when we go to do that, we will bring those electrons in, and what we will end up with is a picture that looks something like this. Again, we're down to only 4 non-bonding electrons there. We will have these guys here that nothing happened to them. Draw them a little bit better there as you see them. And over here. And we put a little bracket around it with the charge on the outside because it's an ion, and that's typically how we draw things that are ions. But more importantly, when we look at this picture, we have now met the octet rule on everybody. And just to show you that is 2, 4, 6, 8 electrons. Guy over here, 2, 4, 6, 8 electrons. Guy up on top, 2, 4, 6, 8 electrons. And now carbon here, 2, 4, 6, and 8 electrons. So it also has 8 electrons. Everybody there now has a grand total of 8 electrons around it. Everybody meets the octet rule. And more importantly, in addition to meeting the octet rule, we have now only placed on this picture still the 24 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons. So we have now fixed the problem, and this is what I was speaking to earlier, that you want to kind of save double bonds and triple bonds to try to fix a situation where you don't meet the octet rule. You don't want a double bond or triple bond out of the box. First off, any questions on that there? Now, again, as I mentioned kind of earlier, you absolutely could have double bonded to the left. And if you double bonded to the left, it would look something like this. And obviously we would have our double bond over here. We'd also put a bracket over like that. And you absolutely could have drew a picture where you double bonded over to the right, and that guy would have looked like this. double bond over to the right. Also do a little bracketing. And these three structures are actually related to each other. And sometimes we put this kind of two-headed arrow in between them. These are what are known as resonance structures. And resonance structures kind of develop in situations where, just like this, there's sort of more than one option where you could have put that double bond. Obviously, we could have double bonded to the left, which gives us that picture on the left. We could have double bonded to the right, which gives us that picture on the right. Or we could have double bonded dead in the center like we did originally there. Each one of these pictures are perfectly fine to draw. If you were asked to draw the Lewis structure for carbonate, you could have drew any one of these three structures. If you were asked to draw all of the resonance structures, you technically would draw all three of these structures with those arrows in between. Why do we get that? Well, it has to do with the idea of that really those double bond electrons. And those double bond electrons, if we just kind of draw it like this, are what are sometimes referred to as being delocalized, which means, you know, at any given point in time, the double bond electrons, like that pair of electrons we brought in to sort of make the double bond, if you will, you know, it may find itself over here, you know, at the top guy, but it then may also be over there. It may be kind of moving this way as well. So, you know, those electrons may be over here at this oxygen, which would be double bonded, maybe kind of moving to the right at that some point, maybe moving to the center guy. And we end up with like resonance structures, and we could draw different resonance structures because in a situation like this, one structure doesn't necessarily adequately describe sort of the situation that's going on. The true structure is probably somewhere between all three of these because, again, those electrons are sort of in constant movement. But again, you don't necessarily have to draw all three of these pictures unless it specifically asks you to draw resonance structures. It just asks you to draw a Lewis structure. Any one of the three would be appropriate. Any questions on that there? Okay, so let's see here. Why don't we, I want to give you some to draw. So why don't you draw, let's see, let's have you draw, why don't you draw SO2? Why don't you draw nitric acid? And I'll give you a hint, nitric acid kind of looks like this. This is sort of how the atoms are arranged. Why don't you draw NH4 plus, H2S, nitrogen, and why don't you draw HCN? All right, so take a few minutes here, draw up some good Lewis structures for these guys, and we will then obviously go through them together here in just a second. Okay, so let's see how we're doing. So why don't we start with the first one here? We'll go with SO2. So again, we're going to start with sort of the valence electrons here. So sulfur is group 6. And there's 2 oxygens, which are also group 6. And that gives us 12 and 6, which is 18 valence electrons. In this case, we have sulfur and we have oxygen. Again, logically speaking here, we have 1 sulfur and 2 oxygens. Sulfur is probably going to be in the middle with the oxygens on the outside. We could probably verify that pretty safely by looking at the periodic table. We see that obviously oxygen is higher up on the periodic table in the same row, the same column as sulfur, which tells us it's more electronegative. So we would want to place our sulfur in the middle, oxygens on the outside. Again, we're going to follow the same procedure here, a single bond to each of the outside atoms. That is 2 and 4 electrons. That gives us 14 more electrons to go. That is going to go on the outside ones until we get 8. So that's going to be 2, 4, 6. That's full. 8, 10, and 12. That is full. Now we have placed 2, 4, 6, 8, 10, 12, 14, 16 electrons.
we actually still have 2 more electrons in pairs that we need to place, and it's commonly missed on this one because people don't follow these rules. So we actually would then go to the center atom and actually place them as dots or lone pairs. And that's how we get the lone pairs here on the center atom, because that is the proper way to place those electrons. At this point, we have now placed all 18 electrons. We need to see if everybody has 8. Oxygen on the outside, 2, 4, 6, 8 is good. Other oxygen's identical, so it's good. But the sulfur here is short. It has only 2, 4, and 6 electrons. It's at this point that we do want to make a double bond and try to fix it. We could do either oxygen, as they are both identical to each other. So remember that when we go to make that double bond, what we want to do is take a pair of electrons from the outside and basically move them in. So I'm going to do the double bond here on the right. I'm going to take these pair of electrons and I'm going to move them in. When I do that, that will get me a sulfur here. We will now have a double bond happening over here and a single bond on this side here. We have now placed 18 electrons on this picture. Oxygen on the left has 2, 4, 6, 8 electrons. Oxygen on the right, 2, 4, 6, 8. Sulfur now has 2, 4, 6, 8 electrons. Everybody here has 8 valence electrons. We have a grand total of only 18. We have our non-bonding electrons where they should go on the center atom because of the way we placed it. We obviously could draw a resonance structure where we double bonded there on the left-hand side. And if we did that, it would look something like so. Any questions on that one there? Okay. So that was SO2. Let's take a looky here at HNO3, which is nitric acid. So it's nitric acid. It has a little bit of a different sort of arrangement, which is why I gave it to you. And obviously, I would give you sort of the connectivity if it was something maybe you wouldn't be able to figure out. We still want to approach it the same way. We want to figure out the valence electrons. So there's 1 for hydrogen. Nitrogen is 5. There's 3 oxygens, each at 6. So that is 18, 19, 24. Looks like. So as I mentioned, the sort of arrangement of this guy looks something like this. And we would follow the same sort of procedure. We're just going to make a single bond to everybody here. Just going to single bond everybody up. There actually is more than one central atom in this case. There's a nitrogen and an oxygen. It's considered central atoms. And we've now used 2, 4, 6, 8 electrons. That gives us 16 more to go. We still follow the same procedure as we did before. We're going to go on the outside atoms and fill them up and then go to the center. Outside atom over here is hydrogen, which we hopefully should know should not get any more electrons because it's done. There should never be dots around hydrogen. So then we would go to the next outside one, which is over here. Do a little 2, 4, 6. Next outside one here, 8, 10, 12. And next outside one is this oxygen. 14 and 16 at this point. Now, by the way, this OH group here is what actually makes it the acid. That's the hydrogen that comes off that makes it the acid, which is why this group is sort of attached like that. We have now placed on there, I believe, all 24 electrons would be better, 24 electrons in this particular case. We want to make sure, again, everybody is good. Oxygen on the left, 2, 4, 6, 8. Same here on the top, has 8. Hydrogen has 2, which is good. This oxygen next to the hydrogen has 2, 4, 6, 8. But again, here we do see that the nitrogen is short. It has 2, 4, and 6. We at this point can make a double bond to try to fix it. There's really 3 options where you could double bond, but probably 2 options are the best, and that would be either to double bond here or here, for the reason I just spoke about, that this is really what makes it an acid. Probably not the best idea to double bond into that. So really one of these 2 oxygens. We want to do the same thing as we did before. We want to basically bring a pair of electrons in to do that. And if we do that, we will end up with something that looks like this, with our double bond up there on top, since that's where I brought my electrons in. And we end up with something like that. At this point, we have now placed still only 24 electrons all the way around: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. And everybody has 8. Nitrogen was the guy that was a little bit short there. So now he has 2, 4, 6, 8. Oxygen above nitrogen with a double bond, 2, 4, 6, 8. Everybody else has 8 except for hydrogen, which has 2. Any questions on that particular one there? Yeah. So that takes care of that one. Now rolling to our NH4 plus. Again, nitrogen here being group 5. There's 4 hydrogens, each has 1. Here we do have a plus. So remember, when something has a positive charge, as we've been talking about, has lost electrons in this case. So that means we actually need to subtract an electron off of there. That's going to give us 5 plus 4 is 9, minus 1 is 8 valence electrons. This one, the nitrogen is going to be in the middle. Remember, hydrogen can never be in the middle, so it's always got to be on the outside. So that makes it pretty simple in terms of its arrangement here. I'm just going to kind of put a hydrogen all around. We can make a single bond to everybody. That now has used 2, 4, 6, 8. That is it. And we need to make sure everybody's good. Hydrogens on the outside have 2, which is good. Nitrogen in the center has 2, 4, 6, 8, which is good. We put a little bracket around it. So there was an earlier question somebody was asking about the bracket. And the answer is, yeah, we typically do put brackets around Lewis structures that for anything that has a charge. Positive charge, negative charge. We typically bracket the structure that we draw, and you should do that as well. And just put the overall charge on the outside top. Again, it indicates that it's an ion and it does have a charge. Any questions on that particular one there? Okay. Takes care of that one. Box that off. All right, we'll go to H2S next. And with H2S, we'll go up here on top, H2S. Again, going to follow the same procedures that we've been doing. We want to go with 2 times 1 for the hydrogen. Sulfur being group 6, that's going to give us 8 valence electrons. Same sort of reasoning as the previous one. We can't really put the hydrogens in the middle. So definitely the sulfur's got to go in the middle. Hydrogens will go on the outside. Again, going to follow the same procedures here. Single bond, that is 4 electrons, tells us we have 4 more to go. And that means that we will fill up the outside ones, but they are hydrogen, which means they're filled already. Now we take those 4 electrons to the center and put them on in pairs. And that would give us 2 and 4, and a grand total of 8. So sulfur has 2, 4, 6, 8. Hydrogens have 2, and that is it on that particular one right there. That would be the correct structure. So again, this is a situation where you do want to follow what we've been talking about. I can't tell you how many times I've seen this picture drawn with double bonds, triple bonds, because again, people just want to kind of double bond or triple bond right out of the box. You don't want to do that. Again, we want to save those things for fixing problems where we don't reach the octet rule. And again, I've seen people draw this without the dots because they're not placing the electrons properly. So if you follow those sort of order like we've been doing here, It allows you to sort of place the non-bonding electrons correctly and end up with hopefully the correct picture. All right, continuing on here, we'll go to N2, which is nitrogen. So obviously there's 2 nitrogens. Each one is 5, I believe. So that is a grand total of 10. In this particular case, unlike where we have a central atom, unlike where we have actually 2 central atoms, by the way, this one, there is no central atom because there's only 2 elements involved, or 2 atoms involved. So this one, pretty much nitrogen next to a nitrogen. And you can still follow the same rules that we did for a diatomic molecule, and it should end you with the right picture. So what do I mean by that? Well, we'll still do our connection here with one single bond, which is 2 electrons, means that we have 8 electrons to go. We'll still place those 8 electrons on the outside ones in pairs. So 2, 4, 6, that's filled, and 2. That is now a grand total of 2, 4, 6, 8, 10 electrons. Remember that at this point, that is as many electrons as I could put on this picture. I cannot draw any more dots or anything like that. So we are in a situation where we want to try to fix it. Obviously, the nitrogen on the left is no good. It has only 4 electrons. Nitrogen on the right, it's okay. It's got 8. So we're going to follow the same things we've done before. We're going to make a double bond. So we'll take a pair of electrons and bring it in. When I do that, I end up with a double bond to this nitrogen and look something like this. If I look at this, I have 2, 4, 6, 8 for the nitrogen on the right, nitrogen on the left, 2, 4, 6. Nitrogen on the left got better, but did not fix it. It is still short. It's at this point where there's no other way I can make another double bond. Obviously, I'm done with double bonds. Now I need to then go to triple bonds. So to make a triple bond, we do the same thing. We're again going to take a pair of electrons and basically bring it in to make our triple bond. When we do, we end up with a triple bond that looks something like that. And each of those nitrogens got the lone pairs that stayed. And nitrogen on the left now has 2, 4, 6, 8. So he's good now. Nitrogen on the right, 2, 4, 6, 8. It is good now. And then we end up with our proper structure for N2, our nitrogen. So again, even a diatomic molecule, as you can see, you can follow the same rules. It will help you get to the right, should it be a single bond, double bond, or triple bond. But again, this also illustrates what I was talking about before. Usually if you have sort of a double bond situation and you make it, and it doesn't fix the problem, you kind of want to exhaust all your double bond possibilities. So maybe there's another way to draw a double bond or somewhere else to draw a double bond. If at some point you do all your double bond possibilities and it still doesn't fix the problem, then you need to kind of go to a triple bond like we did here. Any questions on that particular one? All right, lastly here, our HCN. So hydrogen being 1, carbon being 4, and nitrogen being 5. That looks like, again, 10 valence electrons. So logical arrangement here, hydrogen cannot be in the middle between carbon and nitrogen. Carbon is the least electronegative, so it would be in the middle. And we just kind of arrange it like so. Again, we're just going to follow the same sort of procedure. We're going to make a single bond between the center guy and the outside guys. That is 2 and 4 electrons. That now leaves me 6 electrons to go. We will then put them on the outside ones first. We cannot put any more on the hydrogen, right? Because it's full with 2. That means the nitrogen here is going to get our 2, 4, and 6 electrons. At this point, we are at place 2, 4, 6, 8, 10 electrons. We are out of electrons to place on our picture. We want to make sure that we have now hit 8 electrons for everybody, except for obviously hydrogen here, which is 2. So hydrogen obviously has 2. Nitrogen has 2, 4, 6, 8. Carbon, though, has only 2, 4 electrons. So here again, we're going to try to fix it by making a double bond. We're going to bring those guys in. When we bring those guys in to make that double bond, we end up with something that looks like this, 2, 4, 6, 8, 10. We have now made carbon better at 2, 4, 6, but are still missing 2 electrons. So at this point, there's no other way to make a double bond. Now, just like we did previously, we got to go in and make a triple bond by bringing those electrons in and giving us a triple bond between the carbon and the nitrogen and our non-bonding electrons up on top. So very badly drawn triple bond here. Let me just do that a little better. 2, 4, 6, 8, 2, 4, 6, 8 for the carbon. And we still have maintained the proper number of total electrons. To answer your question, if we look at the periodic table in terms of carbon and nitrogen, we look sort of the arrangement of where that is. So looking at that periodic table, we have boron, carbon, nitrogen, oxygen, fluorine. So remember, electronegativity increases this way, which means nitrogen is further to the right than carbon. And that means that nitrogen should be more electronegative than carbon. Carbon is less electronegative, which is why it's in the center in this particular case. Other questions on that? Are questions in general about drawing Lewis structures. So clearly you need to be able to draw these Lewis structures, things with charges, things without charges. Again, as you can see, hopefully if you follow those rules, you should end up with a fairly good structure when it's all said and done. These are obviously everything that obeys the Octet Rule. We'll talk a little bit about not obeying the Octet Rule in just a sec, but this are your things that do obey the Octet Rule. All right, so now I've been saying things like, you know, you'll end up with a probably a fairly good picture or Lewis structure if you sort of follow these rules. So what do I mean by that? Well, one thing that we also can look at when we draw Lewis structures is something that is what is referred to as formal charge. And formal charge helps us do a variety of things. And as we'll talk about here, one thing that it can help us do, in addition to sort of figuring out, you know, where all the charge is on these elements in these bonds. You know, when we look at something, say like carbonate, for example, that has a -2 charge overall, you may be going, well, where is that -2 charge sort of coming from? You know, is it on the oxygens? Is it on like the carbon? Where is that sort of overall -2 charge sort of coming from? And something like formal charge helps us understand within a bonding situation like what we have here with covalent bonding, they're sharing electrons. You know, in that sort of configuration, certain elements take on almost like a charge in that sort of arrangement of how they are put together. And the formal charge is really the difference between the valence electrons and the isolated atom and the electrons to which they are sort of sharing in your structure. To calculate the formal charge, we use the formula that we see on the bottom. Basically, the formal charge is the number of valence electrons in the free element minus the number of non-bonding electrons. Those are the dots in a Lewis structure. Minus 1/2 the number of bonding electrons, which are the lines in the Lewis structure. And you do this for you could do this for every element that you have in a Lewis structure that you drew, and it will give you basically, like I was saying, sort of, you know, what the charge is on those particular atoms based on how they're sort of bonded together. Again, there's going to be some aspect of sharing of electrons, obviously, in all these, and based on their sharing of electrons, it allows them to figure out the sort of charge that they would have in that situation. So if we look at something, say, like ozone, and we draw ozone here, there's 3 different oxygens. And when we look at ozone, ozone is neutral overall. But you may be wondering, you know, is everybody sort of neutral in this guy? So we could calculate the formal charge for each of these oxygens. So why don't we start with the double bonded oxygen over here. We'll call this number 1 here. We'll do this guy right here. That is the double bonded oxygen. So if we look at the double bonded oxygen and we want to calculate the formal charge on it, it equals the number of valence electrons in oxygen just by itself, which is 6, minus the number of bonding, non-bonding electrons. Non-bonding electrons are our dots. That's a grand total of 4, minus 1/2 the number of bonding electrons. So remember that each of these lines, that represents 2 electrons, that represents 2 electrons. So that would give us a total of bonding electrons here of 4. And that means that the formal charge that we see on this double bonded oxygen here in ozone is 6 minus 4, which is 2, minus 1/2 of 4, which is 2, which is 0. So the overall formal charge that we see here for the oxygen, that's double bonded in this case, is actually 0. Let's take a look at the oxygen on the other side, this sort of single bonded oxygen right here. And if we look at that single bonded oxygen, we would do the same thing. Formal charge would equal, again, the number of valence electrons there are in oxygen, which is 6, minus the number of non-bonding electrons, which in this case is 2, 4, and 6, minus 1/2 the number of bonding electrons, which is obviously the line here, which is 2. So here we would have 2. And that gives us 6 minus 6, which is 0, minus 1/2 of 1, basically, gives us a -1. So what this tells us is this single bonded oxygen here is kind of carrying a -1 charge overall, while the double bonded oxygen on the other side is sort of carrying a 0 charge, again, in terms of how they're sharing electrons and how the electrons are being shared and stuff like that. What about our oxygen that is sitting there dead center, which is this guy? And if we look at this guy, he's got sort of a 2 lines coming in. He's got a couple of dots there and a line that's coming out, basically. And the formal charge here would be 6 minus non-bonding electrons here, which would be 2, minus 1/2 of our bonding electrons, which again would be 2, 4, and 6 in this case here. And that means 6. That is going to be 6 minus 2, which is 4, minus 1/2 of 6, which is 3. So basically 4 minus 3 is +1. So this oxygen with this arrangement is basically carrying a +1 sort of formal charge in this case. Now, overall, when we look at ozone, it's neutral. So even though we have the oxygen on the right with a -1 sort of charge, it is balanced out in this case by the oxygen in the center that has a +1 charge. So +1 and -1 gives you 0 overall. Obviously, the oxygen on the left is 0. So that's why When we add up these formal charges, they should equal the overall charge that we see in a particular compound, which in this case is 0 overall. Question on sort of how to calculate the formal charge there. So why don't you try one here? Why don't you calculate the formal charge on all of the elements here, the carbon and the 3 oxygens that we see here in carbonate. So take a moment or two, calculate the formal charge for the carbon and the 3 oxygens in carbonate, and we'll talk about it here in just a sec. Take a look, and why don't we just start with let's go with the single bonded oxygen. So if we do our single bonded oxygen, again, the formal charge here would be 6 because that's what number of valence electrons there is in just oxygen by itself. Minus, there is 2, 4, 6 of the non-bonding electrons, these guys. Minus 1/2 the number of bonding electrons, which is that guy right there, which represents 2. So again, that's going to be 6 minus 6, which is 0, minus 1/2 of 2, which is minus 1 in this case. So this oxygen here is carrying a -1 formal charge. Oxygen on the right-hand side is identical, also carrying a -1 formal charge. If we look at our double bonded oxygen, much like what we saw in the previous example, and as you could kind of see, perhaps it will come out the same. That's going to be 6 for the oxygen, -4 for the non-bonding electrons, minus 1/2 of 1 and 2 lines, which represents 4 electrons. So 6 minus 4 is 2, minus 1/2 of 4 is 2, and that gives us a formal charge of 0 for this guy. Lastly, we have our carbon, which is double bonded up there and single bonded happening. For our carbon, the formal charge is 4 for carbon, as that's the number of valence electrons, minus 0 in this case. There's absolutely no dots or non-bonding electrons there. Minus 1/2 of basically 2, 4, 6, 8. Again, each line represents 2 electrons. Gives us 8. 4 minus 0 is 4. Minus 1/2 of 8 is 0 in this case. Formal charge there on the carbon is 0. So when we talk about really the -2 charge overall for carbonate, it really is coming from these 2 oxygens on the outside. Basically have a -1 charge each. -1 gives us the -2 charge that we associate with carbonate. So really, again, that -2 is coming from those single bonded oxygens in this arrangement that we see in carbonate. Any questions on that there? Okay. So we can calculate the formal charge on each of these elements in these particular Lewis structures. And again, you may be saying, what's the purpose of this per se? Well, other than, sort of determining sort of where the charges sort of lie, like we did here, we know now that it is actually the single bonded oxygens that are carrying those negative charges that give carbonate in this arrangement an overall charge of -2. We can also use formal charges in Lewis structures to help us decide between 2 different structures that you may draw. And if you draw in Lewis structures before, you know that maybe just depending on how you kind of put it together or arrange it, you can end up with multiple sort of pictures. And maybe some are good and some are bad. And formal charts could help us make a determination of, what Lewis structure may be more likely to be good or a better structure than one that's maybe probably not going to happen. It's not the best structure between the 2. So ultimately, when we sort of draw a Lewis structure and we calculate these formal charges, the idea here is the most sort of best situation that you could have is one really where pretty much nobody has a formal charge, like everybody's at 0. So that's like sort of ideal situation. And that's probably going to be the best structure that you could draw if you go around and everybody ends up with 0 in terms of formal charge. When we get formal charges of 2s and 3s, those are probably less likely to occur. Again, the idea of bonding is to sort of minimize everything, minimize charging, minimize, overall charge. And again, if we end up with like 2s, 3s, 4s, or anything larger than that, it's probably not the best structure. If you have sort of a similar distribution of formal charges between two different structures, the more possible one or plausible one is one where the more negative formal charge is on the more electronegative atom. So a more negative formal charge on the more electronegative atom is one that we would expect. So let's see how we could kind of use that here. Let's take formaldehyde, for example. And if you hook up formaldehyde, maybe this is a couple of different ways you may decide to draw formaldehyde. So why don't you take a moment here and figure out the formal charge on everybody and decide which one you think would be the better picture based on formal charge, better Lewis structure. So take a moment here and do it, and then we'll talk about it. Okay, so since we're kind of to the end here, let's take a look and sort of see what we come up with. So we'll start with guy on the left here. Hydrogen basically is this guy. So it's basically 1 minus 0 minus 1/2 of 2. Again, the line has 2 electrons. That's 1 minus 1/2 of 2, which is 1. That is a formal charge of 0, which means this hydrogen here has a 0. This one, which is identical to it, also has a 0. We go with the carbon there, which looks something like this. Formal charge here would be 4 minus 2 for the non-bonding electrons, minus 1/2 of 246 in that case. That is going to give us 4 minus 2, which is 2, minus 1/2 of 6, which is 3. So that's 2 minus 3, which is minus 1. So the carbon here would be carrying a minus 1 formal charge in this arrangement. If we look at the oxygen, which has this arrangement here, oxygen is 6, so that would be 6 minus 2 minus 1/2 of 6. That gives us 6 minus 2, which is 4, minus 3, which is plus 1. All right, so not terrible per se. We got some zeros in terms of formal charge. We got some 1s happening here. Let's take a look at the other possible way you could have put this guy together. Hydrogen will come out the same as what we had before, so that's going to be 0. This is going to be 0. We've done the double bond oxygen, but again, if we look at it, it is going to be 6 minus 4 minus 1/2 of 4, which is going to give us 0. 6 minus 4 is 2, minus 2 is 0, which means this oxygen is carrying a 0 formal charge. And the carbon here in the middle basically has that arrangement, and that's going to be 4 minus 0, there's no dots, minus 1/2 of 8, and that will give us a formal charge of 0 here. Now, you could have perfectly drew both of these structures, and sometimes people ask, well, why can't I attach the hydrogen to the oxygen? Well, in this case, the guy on the right would definitely be the better structure, right? It's pretty much zeroed out everywhere. We sort of have minimized formal charge on everybody here. The guy on the right, not terrible, but one other thing that's not so great here is when we look at this -1 distribution to this +1 distribution, and we look at carbon and oxygen, oxygen is the more electronegative atom, but it has the more positive formal charge. And again, that's another bad sort of situation. So based on all those things, if you had to choose between these two structures, which one would be best based on formal charge, it is this guy. Again, minimizing that overall formal charge. Any questions on that? And that's why, if you've ever drawn those structures before, maybe you've asked, like, why can't you sort of bond this to this and this to this? And some of the reason has to do with sort of formal charge. based on formal charges, one structure might be better than another structure you may be able to draw. Any questions on that there? All right, we will lay it up there for today in terms of lecture.